All right, good morning. Hope you're all doing well. We are going to continue with chapter 5, which is on compounds and nomenclature, which is just a fancy way of saying naming, specifically naming compounds. I'm going to take a quick look at the syllabus together just so that we're all on the same page. So you should have finished your last exam on Sunday or Monday. Homeworks and labs should be turned in regularly. So we're sitting here in week 5. So this week we'll do naming and nomenclature, and next week we will as well, just so that we can get more than enough practice. And then you'll have 2 more chapters. So your next test isn't until the beginning of March, and I'll give you guys a couple of reminders, but you've got a little bit of a break there, a couple weeks there. And then, yeah, the tests are sort of going to come every month. So, okay, so nothing super crazy for this week. It looks like because chapter 5 is broken up between the next 2 weeks, you won't have any homework due this weekend. You shouldn't have a Mastering Chemistry due on Sunday. So don't stress about that if you're not seeing anything showing up. It's due the following week. If you want to complete it early, you can, but you will have an experiment. So yeah, don't forget that. Okay. So back to naming and nomenclature. So we had talked about polyatomic ions and how, where are you, mouse? There you go. Keeps disappearing on me. So we had talked about all these polyatomic ions that, when I'm talking about, for instance, nitrate, if I say the word nitrate, I'm not talking about nitrogen. I'm talking about N nitrogen with 3 oxygens that has an overall minus charge. So the definition of nitrate is NO3 minus. The definition of ammonium is NH4 plus. These things don't change when you're giving that or using that appropriate name. And just like we flip-flop charges for the metal and a non-metal, we can flip-flop charges for a metal and a polyatomic ion. If you look, most of the polyatomic ions have negative charges, right? So most of them are going to behave as the non-metal thing. There is one that has a positive charge, ammonium. Do you see how it's NH4 plus? That can take the place of a metal or the positively charged cation. Let's do a couple more of these. For something else. Okay, so I want you to combine, so have a polyatomic ion sheet or your cell phone available. I'm going to give you a couple things I want you to combine. So let's do potassium. Ooh, it's like really, it's a little too much for me. Bring that down a notch. Let's do potassium and carbonate. Let's do aluminum and nitrate. Let's do magnesium combined with sulfate. I'll give you one more. Ammonium combined with nitrite, NITE. So one thing to remember, if you're seeing things ending in ATE or ITE, you want to check your polyatomic ion sheet. Okay, that's a good indicator that it's a polyatomic ion. So I'll give you a minute per problem. So 4 minutes for that. Obviously, while you're working on it, if you have a question, turn your mute off and I can help you out, or throw it in the chat and I can address it. But we will go over these in 4 minutes. And if you are needing a polyatomic ion sheet too, you can literally just on your computer, go to Google and type in polyatomic ions and it'll pull up something in the images, the Google images. All right, so when coming up with the formula from these two things, again, you want to make sure that it is ionic. So it's some sort of metal combined with a non-metal. Polyatomic ion is behaving as the non-metal. For this one down here, you can treat ammonium as a metal. These, because they're charged particles, they're going to do the same thing. So we've got potassium and carbonate. So start off by writing the symbol with its appropriate charge. So potassium gets a 1+. Why? Because it's in column 1 on your periodic chart, okay? Carbonate, CO3, and its charge is 2-. Why is it 2-? Because that is just the definition of carbonate. If you're going to write the word carbonate, this is what you have to refer to, and it includes the charge. Sometimes people will just like memorize or be familiar with the number of atoms. So it's a carbon and 3 oxygens, and they totally forget about the charge. Don't do that. With a polyatomic ion, the charge is just as important, okay? So we're going to flip-flop. So this 2 is going to get dropped to the potassium. So we need 2 potassiums. The 1 gets to the carbonate for every 1 carbonate. We don't need to put carbonate in parentheses if we only have one of them. Aluminum nitrate. So aluminum Al with a 3+ charge. Nitrate NO3 with a -1 charge. Flip-flop, that would tell me I have 1 aluminum for every 3 nitrates. So I'm going to put nitrate in parentheses. Anytime I have more than 1, I need to parentheses it and then put the 3 on the outside. Sometimes this bothers people because they're like, oh, there's a 3 here and there's a 3 here. What's going on? That's okay. Don't get stressed by that. Or if you see a 4 and a 4 or a 2 and a 2, you can double it up. Magnesium sulfate. Magnesium is Mg with a 2+ because it's in column 2. Sulfate, SO4, 2-. The more you use these, the more you're going to get comfortable with them. So we're going to flip-flop charges, 2 and 2. So it would be Mg2SO4, 2. Now, because we're dealing with something that's ionic, we want to reduce. So the 2 and the 2 are going to disappear because we're going to divide each one by 2. And that will lead us to MgSO4 to refine it. The last one here, ammonium nitrate. This is 2 polyatomic ions that are coming together, but they're both charged, so they're behaving as an ionic structure. So we've got NH4+ with NO3-. This is a plus, this is a minus, a 1 and a 1. So we just kind of smush them together. So NH4+, oh no, I'm sorry, ditch the plus. NH4, NO3. Another pitfall that I see students doing when working, not even just with this, but even with like the simple one metal, one non-metal, is that they want to like bring these charges down somehow. They want to put like a plus here, you know, or a 3 here. What's happening when these things come together, when this bonds together with this, the charge disappears on that. So we end up getting something that is actually charge neutral, right? The positive balances out the negative. So if I was to put a charge in the upper right-hand corner for this whole molecule, it would be 0. So don't bring the charges down. That's why we're balancing out the number of atoms so that we can get something that's charge neutral. Okay. So for ionic, once you've combined them together, your final molecule for each of these should in fact be something without a charge, charge neutral. Any questions on that, on combining polyatomic ions with like a metal or non-metal? Kind of just if you want to have the polyatomic ions available. If you don't have them available, it makes it a little trickier. And be thankful that you don't have to memorize those, because traditionally I would have you guys memorize, but because of the nature of the semester, we're not going to do that. Okay. So you can write the formulas now. So what we're going to move into is naming the compounds. Or this thing called nomenclature. So there are so many compounds out there. Like with elements, there's only 118. So at some point as a chemist, you can just memorize them. But there's so many compounds out there that to memorize their everyday names would be kind of exhausting. Usually chemists within whatever field they're working in will know the everyday common names for them. But for all the other stuff, they need to have some sort of systematic way to name compounds that's consistent so that doesn't matter what compound I throw at you, you can name it and you can know what's in it. There are specific rules that you follow in order to name these things. And once you've learned the rules, you can name anything. Now, we're not going to do organic naming. We're just going to do inorganic, or things that don't have carbon, hydrogen, oxygen as their center focus. Now, do know that many compounds have common names. So H2O, its common name is water. That's a common name that you do need to know. But if we were to follow the systematic naming structure, we would call this dihydrogen monoxide. Di meaning two, so two hydrogens, mono meaning one, monoxide, okay? And I will teach you those rules a little bit later. Since water is such a familiar compound, we know the everyday name for that. How do you learn the everyday common names? You just have to do that through familiarity. We don't have enough time for you to get familiar with all 55,000 compounds or whatever that are out there. So we're going to learn the system. So the system with naming, actually, I'm going to drop down to the very last page here, or almost last page of the slides. So this is a really great flow chart to have when you're naming things. You may want to print it out. You start at the top. The very first thing that you need to do when you're going to name something is decide, is it ionic? Is it molecular? Or is it what we would call an acid? And we haven't talked a whole lot about acids. We'll get into that in a little bit. So for now, let's just stick with these two. So remember, if it's ionic, it means it's a metal combined with a nonmetal. If it's molecular, it's two nonmetals. So look at your periodic chart, find your zigzag line. If it's two things to the right of it, that's molecular. If it's one on the right and one on the left, that's going to be ionic. So that's our first step, is determining that it is in fact ionic. Now, if we've decided that it is ionic, what are we going to do? Let's go back up here. So we want a metal combined with a nonmetal. So if you've determined it is ionic, then you have to decide, is it a metal that forms only one type of ion, or is it a metal that forms multiple types of ions? That means, is it one of the metals in the main groups with a predictable charge, or is it one of the transition metals with an unpredictable charge? So let's just put predictable charge and then unpredictable. So examples of metals that are predictable charge, lithium. What's lithium's charge? If you look at the periodic chart, it's a plus. What's aluminum's charge? Aluminum's a 3+. What is zinc? Even though zinc sits in the transition metals, I told you I wanted you to treat that with a predictable charge of a 2+. Right, so all the ones in column 1, column 2, column 3, and then there's a little dusting in the middle, have predictable charges. Which ones have unpredictable charges? Chromium. What's its charge? Well, I don't know. It can change. Cobalt, lead, Pb. All of these have varying charges, okay? So that's your next step. Does it have a predictable charge? Does it have an unpredictable charge? Gabby, hold on one second. Gabby, I am working. Miss Brittany can help you tie them. I have to work. Please go. No. She's right there. Gabby, come on, hon. Please close my door. Sorry. She wanted me to fix her. One of her Barbie's legs keep falling off. I have to keep putting it back on. Okay. So let's start with sometimes it's called type 1. The ones that have predictable charges, you'll see it referred to in your text as type 1. The unpredictable charges, they'll call type 2, transition metals. You can see here, this gives you a little note that says zinc and silver have predictable charges, right? So aluminum is the 3+ on your periodic chart, go down into the left. Zinc is the 2+, go down into the left. Silver is the 1+. And then lead and tin have unpredictable charges. So there's some of the predictable charges. Scandium also is a 3+. So if you want to put a little note in there that that's a 3+ too. Here are some of the different charges for the transition metals. Don't write these down, okay? You don't need to memorize these. But like, for instance, chromium. Chromium sometimes likes to form a 2+, sometimes it forms a 3+. How we would name it is I would say chromium, and then I'd put a Roman, in parentheses, I'd put a Roman numeral with whatever that charge was, okay? So if I'm dealing with chromium 2+, I would call it chromium Roman numeral 2. If it's chromium 3+, I'd write it as chromium 3. So you do want to know your Roman numerals up to like 10. Down here for lead, we've got lead 2+, so that's lead 2, and we've got lead 4+. So we've got a little IV for 4. So that's how you indicate which charged particle you're working with or charged atom you're working with, because cobalt 2+ is going to do different things than cobalt 3+. Think about when it combines with a nonmetal, you have to flip-flop the charges, right? So if the charge is different, you're going to get a different thing. And we'll do a bunch of practice with that. So the simpler one, the type 1, which is sometimes called binary ionic compounds as well. This is where you just have a metal with a predictable charge and a nonmetal. We name it like this. You say the name of the cation, which is the metal, just name the metal. You take the base name of the anion, so you chop off the end of it and you IDE it. So we don't call table salt sodium chlorine. What do we call it? Sodium chloride, right? So sodium and chlorine come together to form sodium chloride. So get in the habit of when you see IDE at the end, it's talking about the element chlorine. When you see ITE or ATE, those are polyatomic ions. So I want, let me show you. Let me show you a couple things because this always mixes people up. So I'm going to write sulfide, like this is attached to something, some sort of metal. Sulfide, sulfate, and sulfite. So all three of those sound very similar, right? And sort of the default at times, especially if we don't have refined skills with naming, is to be like, oh, they're just all talking about sulfur. Well, they're not all talking about solely sulfur. They do all contain sulfur. This one here, the IDE is indicating that we're talking about the element. So this is in fact the S, okay? ATE and ITE are polyatomic ions. So sulfate is SO4 with a 2- charge, and sulfite is SO3 with a 2- charge. So just be careful about what's happening with the endings when you're looking at your names, because if I say aluminum sulfide versus aluminum sulfate, those are not the same thing. Aluminum sulfide is Al2S3. Aluminum sulfate is Al2SO4, 3. Okay, so different things. So as far as how we truncate these, fluorine goes to fluor, chlorine goes to chlor, bromine goes to brome. Most of them make sense. One that's gets cut off a little bit more is oxygen. Oxygen cuts to ox. Okay, so it's not oxygenide, it's oxide. Right, so it gets truncated a little bit more than the other ones. Sulfur, sulfide, nitrogen, nitride. And so these are all the anion names. So that's not too bad, right? As far as naming, you just name the metal and then you IDE the non-metal. So if I write something like this, CaCl2. This is a metal and a nonmetal, so it's ionic. This has a predictable charge, so it's type 1. So all I have to do is name the metal, calcium, take the abbreviated or the truncated version of the last thing, chlor, and IDE it, calcium chloride. Na2S, this is also ionic. It's type 1. So I just say sodium. And I say sulfide. See how these have like 2 in them here because we have multiple atoms. You don't have to translate that over here in any ways because the goal is to write a name that is as slimmed down as possible, but has all the information you would need or retain. So with this, is this enough information to get back to this exact formula? And it in fact is. Calcium is Ca with always a predictable charge, chlorine, Cl with a minus flip-flop, I get CaCl2. So I can in fact go back, so I've used enough. Times we don't want to use this system, CO2. This is not ionic, it's molecular. So we don't follow this system. So Na, not applicable currently. I will teach you the rules on how to name this one towards the end of the chapter. All right, so I'm going to give you some type 1s. I want you to tell me what the name is. Al2O3, ZnF2, Li, and Rb3p. So using the system that you've got so far, name those. Okay, so each of these, I'm just gonna right off the bat check and make sure, okay, this is a metal, this is a metal, 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 and they're all predictable charges. So this first one is aluminum. We always name the metal first, and then we take the non-metal, we truncate it and we IDE it. So aluminum oxide. Here we've got zinc. We truncate the second thing, zinc fluor, IDE. Lithium iodide. Sounds kind of strange, but that is the correct pronunciation. And then we've got rubidium. And then it's phosphide. Okay, so all of those IDEs indicating that we're dealing with the element. I'm going to jumble a couple of these together going the other direction. And I want you to write a formula. So calcium nitride, magnesium nitrite, and zinc nitrate. Now, I want you to write the formula for each of these. And always let me know if my handwriting is difficult to read. This one's an IDE, this one's an ITE, and this one's an ATE. I'll give you 2 or 3 minutes. Okay, you there? If you've got another minute, go for it. Of work, go for it, because I'm going to help out when student Sarah says, can you show again how you would know the numbers of each atom just from this name? For example, Al2 with a 3 plus and O3 with a 2 minus. Okay, so I'm going to do that exact one. So Sarah, if we've got aluminum oxide, and we want to solve for this, figure out what its formula is. Aluminum always has a 3 plus charge. It forms a predictable cation. Hopefully you have that written on your periodic chart. Above the column where aluminum and gallium are, you have a 3 plus there. Oxygen, this is oxide, oxygen always has a 2 minus charge. That's what it likes to do. It likes to eat up 2 electrons. Oxygen is in column 6. Hopefully above your column 6, you have a 2 minus charge. If you don't, talk to me after class and I'll fill you back in on what those charges are. So what the simplest way, you're trying to balance it out. You're trying to come up with a final molecule that's charge neutral. And so you need to find the lowest common denominator between the two of them. And the fastest way to do that is to take the magnitude of this thing. So the 3 of this is going to get dropped down and become the subscript of the oxygen. The 2 on this is going to become the subscript of the aluminum. So aluminum gets the 2, oxygen gets the 3. And then it's charge neutral. And you can go back and check and see, okay, if aluminum always has a 3 plus charge and I have 2 of them, 3 plus times 2 equals a 6 plus, right? Oxygen always has a 2 minus charge and there's 3 of them. Multiply that, that means it's a minus 6, plus 6 and a minus 6 will cancel out and you have a charge neutral molecule. So if you have some more questions with that, Sarah, feel free to stay after class and we can go into a little bit more detail. Okay. So these guys here, so you're going from the names to the formula. And now that you know how the naming system works, when you see something that says calcium nitride, that is combining calcium that always has a 2 plus with, when they say nitride, they mean nitrogen. All right, so N with a 3 minus charge. Again, those are coming from the periodic chart, depending on what column it's in. So now we're going to flip-flop. The 2 is going to get dropped to where the nitrogen subscript is. The 3 is going to get dropped to where the calcium subscript is. So it should be calcium with a 3 and nitrogen with the 2. There and there, flip-flop. Magnesium nitrite is not talking about just nitrogen. This is a polyatomic ion. So we've got magnesium, which is always Mg with a 2 plus. Nitrite is NO2 with a minus charge. Flip flop, the 1 here, the magnitude 1 here tells me how many magnesium I have. So I've got 1 magnesium. The 2 is going to be applied to the entire nitrate molecule. So I'm going to put that in parentheses, NO2, and I'm going to bring that 2 to the outside. Zinc nitrate, again, when you see ATEs or ITEs, you want to just check your polyatomic ion sheet. Zinc is a metal with always a 2 plus charge. Nitrate is NO3 with a minus charge. From there, we're going to flip flop. So zinc, I get 1. Nitrate, I get 2. So NO3 with a 2 on the outside. So these little details, right? This IDE, ITE, ATE, it makes a huge difference. The formula totally changes. So just always be asking yourself, is this a metal? Does it have a predictable charge? Is there a polyatomic ion anywhere in here? Now, what happens if we have one of those pesky transition metals? Okay, so a binary ionic compound, binary just meaning two things, like a binary star system. So a metal with a non-metal. What if the metal has a varying charge? Well, then you have to give the reader an extra piece of information. So you can't just say like copper oxide. You have to put in parentheses after the copper, are you dealing with copper with a 1 charge or a 2 charge or a 3 charge? So the system is, so let's say we have copper here. If it's copper with a +1 charge, you're gonna write copper 1. We don't drop the 1 with our charges, okay? So always make sure you're writing that out. Copper with a 2+ is copper 2. Now this number here in Roman numerals is talking about charge, not how many you have. So it's not saying, like when I say, if I said copper 2 oxide, I'm not saying, oh, I have 2 coppers. No, 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 no. What I'm saying is I'm dealing with copper with a 2+ charge and oxygen with a 2-, and from there we'll flip flop. Okay, so this is talking about charge. So when naming, the system is very similar to the last one, but we just add the Roman numerals. So you say the name of the cation, which is the metal, so list the metal. In parentheses, put the charge of the metal, take the base name of the anion, and ide it. All right, so it's the exact same, except there's a Roman numeral in it. So let's look at FeCl3. Actually, we're going to do a couple. We'll do FeCl3. We're going to do FeCl2, and we're going to do FeCl. This would be a group called iron chlorides. Okay, so all of these are a type of iron chloride, but they're different, right? This is a 3, this is a 2, this is a 1. And by now, hopefully, you're understanding that subscripts make a big difference, right? So if you change the number of something, its properties will shift. So when naming these, I see, okay, this is a metal, and I'm just gonna write the name of the metal. This is iron. I'm gonna put a parenthesis because iron has an unpredictable charge, and I'm gonna come back to that. What is this thing here? This is chlorine, so I'm gonna say chloride. Right, so it's some sort of iron chloride. And in fact, all of these are an iron chloride. So this one as well is iron. Iron has an unpredictable charge, so I'm gonna put that in parentheses, chloride. And then this one here as well is iron with some sort of charge that we'll come back to, and chloride. So I have 3 different types of iron chlorides. So as if I was to write the name, it's not enough to just say iron chloride like this. If you told me this, I can't write a formula. Why? Because I'm going to write chlorine. Whoa, where am I? Chlorine with a minus charge, iron, and I'm going to go, what's its charge? There's nothing here. I can't write a formula, so we don't ever want to simplify it like that. So let's figure out what its charge is. What do we know about the whole molecule? The whole molecule has to equal a 0 charge. So I'm going to sort of put a squiggly line through this to separate out my metals from my non-metal. Now, everything on the metal side, charge-wise, all the positive charge needs to equal all the negative charge. So what you do is you go from what you know for sure to figure out what you don't know, because right now the charge on this is a question mark. So what is the charge on chlorine always? Look at your periodic chart, decide it's in column 7. What did you write above that? -1, right? So every chlorine, doesn't matter what it is going to have a -1 charge. So I'm going to put -1. How many of them do I have in this situation? Well, in this first situation, there are 3 chlorines. So I need to take that -1 and I need to actually multiply it by 3. So what's my overall negative charge? It's a -3 or a 3-. Well, what balances out a -3 to give us a 0? A +3. So you go from what you do know to get what you don't know. So if this is a +3, that becomes the charge of this iron. It's a +3. So I'm going to put in here 1, 2, 3. Or I would call this first thing iron 3 chloride. Let's look at this next one. So I'm going to sort of cut it in half. I know the whole thing has to equal 0. Chlorine is still a -1. That hasn't changed. What has shifted, though, is that there's only 2 of them right now. So instead of multiplying it by 3, I'm going to multiply by 2 for a -2 charge. If this is -2, what does this have to be to balance it out? A 2+. So this is iron 2 chloride. This final one down here, hopefully you're starting to see a system, also needs to equal 0. What's chlorine's charge? Chlorine's charge is always -1. How many do I have? I just have one of them, so it's multiplied by 1, so it's a -1. So what does iron need to be to balance that out? A +1. So this would be iron 1 chloride. So anytime you're dealing with something with a transition metal, it's not enough to just say it's iron chloride. You have to say it's iron 2 chloride so that you get the correct formula. I'm going to give you a set of oxides. Let's do cobalt, COO, COO2. And then I'm going to have you try this one. This last one's going to be a little tricky. CO2O. Try it. If you don't get it, don't stress too much. We'll go over it. So I want you to name each one of these. CO is cobalt. These are unpredictable charges, so you are going to have to calculate the charge. I'll give you all 3 minutes for that, and then we'll go over it. Okay. Again, getting in the habit of seeing this is in fact a metal and a non-metal. It's a metal with an unpredictable charge, so it's a type 2. Type 2 ionic. In the beginning, it may help you to write yourself little notes like this, just because, it's easy when we go section by section. It gets much more difficult when everything is sort of jumbled together. So you always want to identify what are you working with. So if this is a type 2 ionic, I need to name the metal first, cobalt. And then I know it's unpredictable, so I'm going to put my parentheses in. I'm just going to come back to it. And this thing here is oxygen. So that's going to be oxide. And in fact, because I group them together like this, all of these are some sort of cobalt oxide. Cobalt oxide, cobalt oxide. Will they always be clumped together like that? Like on a test and stuff where you have like 3 of them? No, I'm just doing it so you can see how they differ by subscripts and things like that. All right, so this first one, I'm going to put a little squiggly line between. I know this whole thing needs to equal 0. So what is the charge of oxygen? Always. Oxygen is in column 6. It should always have a 2- charge. Actually, let's just write the 2-. In this case, how many of them do I have? I have 1. So I'm going to multiply it by 1. So when you're going down, you want to multiply. When you're going up, you want to divide. And we'll see that on this bottom one here. So if I'm going from this down to the charge, a 2- times 1 will give me a 2- charge. So what does cobalt have to be? 2+. All right, so this is cobalt 2 oxide. What about this one here? All right. Still needs to equal 0, still dealing with oxygen, so it still has a 2- charge, but we've shifted it. We've actually doubled the number of oxygens we have. So I need to multiply it by 2. This is going to have then a 4- charge. What will cobalt be? It'll have to be 4+ to balance it out. So IV. Any questions on that? No? Okay, this one down here. So what is different about this one than all the other ones we've looked at? In every situation, we've had only one metal, right? 1 iron. Here we've had 1 cobalt. In this case, we have 2 of the metals. So I'm going to put a line through this. It needs to equal 0. Oxygen is a 2-, and how many are there? There's 1. So I'm going to multiply it by 1. So 2-. So what does the total charge on this side have to equal? Well, if this is 2-, this has to be a 2+, right? But I need to take into account that there are 2 cobalts. So I actually have to divide by however many cobalts I have. So the 2+ is coming from 2 cobalts. So what does each cobalt contribute? Each cobalt contributes a +1, right? +1 and +1, add those together. That will give me the 2+. So this is actually going to be cobalt 1 oxide. What happens so often is people will see that 2 and they don't even acknowledge that there's, multiples of those, and they go, oh, it's cobalt 2. But let's write out cobalt 2. Cobalt, and this is a great way to check if you've done it, right? Cobalt 2 oxide, if that's what you had established here and you're like, I don't believe you, I want this to be cobalt 2. All right, well, let's see if you're right. So cobalt, cobalt will have a 2+, oxygen will have a 2- flip-flop, CO2O2, those reduce to COO. Did you come up with the same formula? No, you didn't. They don't have the same superscript or subscripts rather. So something went awry there. Probably what happened, if you ever go to check, is that you didn't divide it by the number of metals. Cobalt 1 oxide, let's try that out and make sure that we are in fact correct. So cobalt 1 would mean that cobalt has a 1+ charge. It means that oxygen has a 2- charge, flip-flop CO2, 1. And look at that, bam, bam, it's the same thing, All right, so we can go interchangeably. What I see often, pitfalls with this, is when people see this number in parentheses here. So let's say, you were going backwards, they'll see the 1 and they think, oh, that means I have 1 cobalt and an oxygen, right? The 1 is just coming down as the subscript. That is not the case, all right? This always refers to charge. Charge, charge, charge. So let's do that. Let's go from this way and go back to the formula. Because you're going to have naming stuff that's going from the formula to the name, and then some from the name to the formula, and then molecular and ionic and binary and polyatomics, and they'll be all sort of jumbled together. So nickel 3 oxide. Let's do lead 2 nitride. And I'm going to have you do titanium 1 bromide. Okay, so I want you to go from the name and then go ahead and write a correct formula. I think this way is much easier than formula to name. And I'll give you 2-3 minutes for that. Okay, so if you've got a name and you're trying to write a formula, nickel, so you write the symbol for nickel, Ni, and then you may just sort of instinctually go to your periodic chart and think, oh no, its charge isn't there. What is its charge? Well, that's why it's written here, right? That's why you have to put some sort of number there. That indicates that you have a 3+ charge. It does not tell you that you have 3 nickels. It tells you its charge. So first write out the cation and the anion, or the metal and the nonmetal, with their charges. Oxygen always has a 2- charge. You'll start to learn the predictable ones pretty fast. Then we're going to flip flop. So nickel is going to get the 2 and oxygen is going to get the 3. Next one, lead 2 nitride. Lead is Pb. It has an unpredictable charge, but it's denoted here in this given example. So it's a 2+. Nitride is IDE is talking about nitrogen. So nitrogen always has a 3- charge. Flip flop, and we will get 3 leads for every 2 nitrogens. This last one, titanium 1 bromide. And again, we don't leave off the 1. If you have a charge of 1, you still have to indicate it. Sometimes, like, you know, with the number of atoms and stuff, we can assume. We don't assume for that. So titanium is Ti. If you, again, were to go to the periodic chart, you'd see it's in the transition metals. There's nothing you can pick from it, but it's sitting for you right there. So this is a 1+. Bromine, bromide is talking about bromine, that's Br, and that always has a 1- charge. It's a 1-to-1, flip-flop, Ti, Br. Okay, how are you feeling about that? Outside of, like, you know, we want to practice and we need to do some homework, and I will definitely be giving you guys all these things sort of jumbled together. But how is that charge neutrality working for unpredictables? If you have questions, if you're wondering where am I getting numbers from, let me know. Okay. So just like with the type 1s, or the predictable charges in polyatomic ions, we can combine unpredictable charged metals with polyatomic ions as well. So like this one, for instance, I've got potassium nitrate. This is a predictable charge combined with a polyatomic ion. We would call it potassium nitrate. This thing here, FeOH2. This is an iron, and then this OH is a polyatomic ion. So if you ever are looking at a name and you're like, oh my gosh, there's too many atoms. Like, I thought it was just one thing and one thing. This has 3 things. It's because it's a polyatomic ion. So you want to reference that. So this is iron, and this thing is called hydroxide. So it's iron hydroxide, and we have to put a charge in it. Well, hydroxide, this polyatomic ion, always has a 1- charge, and there's 2 of them. So we do our system. We have an overall 2- charge, so my iron has to be a 2+ to balance it out. So you do the same thing, but you just use a polyatomic ion. So I'll do one of those for you. Cu, NO2. So there's a couple things going on here. I've got a metal and it has an unpredictable charge. So this is copper. I'm just going to write out copper. And then it has an unpredictable charge. So let's put a Roman numeral. And then we have this thing. This is called nitrite. So I'm just going to write nitrite. With your polyatomic ions, you just say the name. You don't truncate it and add IDE. You just say whatever it is. So like, for instance, LiCO3, this would just be called lithium carbonate. I think I didn't specify that, so I want to do that. So you just say the polyatomic ion name. Don't need to change it or anything. All right, so back to this one here. So we've got a metal with an unpredictable charge and a polyatomic ion. We've got the base of our thing written out. Now we need to figure out the charge of the copper. So we go from what we do know to get what we don't know. So this whole thing needs to equal 0. What is the charge of one nitrate or nitrite molecule? It's always a 1- charge. Where do you get that? You get it from your polyatomic ion sheet. Now, how many of these little packets are there? There's 2 of them. So I need to multiply it by 2 for an overall 2- charge. So what does the copper have to be? There's only 1 of them, so it's got to be a 2+. Copper 2 nitrate. Same system. You just have to make sure you're treating the polyatomic ions as a packet. So I'm going to give you 2 of those to do. Let's say we've got Ti2 SO4 and PB, OH3. Okay, so name each of these. Okay, so this first one, I've got a metal and a polyatomic ion. I'm gonna say the metal's name, titanium. Titanium is unpredictable, so let's put the parentheses in. And then I've got this thing, which is sulfate. And I just say the name sulfate. I don't have to change anything. So now I need to figure out what the charge is of titanium. So let's sort of splice our metal and our non-metal section in half. Whole thing needs to equal 0. Well, what is the charge of sulfate? And this is just one sulfate. This is not 4 sulfates. And this 4 does not indicate its charge either. So this whole thing has a 2- charge. It's hidden because it's being combined with this thing to give an overall neutral charge. So you need to look that up. So 2-, how many sulfate packets do we have? We only have one of them. So that is an overall 2- charge. So what side, or what does the charge have to be over here? It has to be a 2+. But how many titaniums are there? There's 2 titaniums. So I have to always divide by the number of metals I have. Now, a lot of times you only have 1 metal, so you don't have to go through that process, but here we do. We have to take this 2 and we have to divide it by 2 titaniums. So each titanium is giving a 1+ and a 1+, right? So this titanium has 1+, this titanium has 1+. They come together to give you the 2+. So we would say this is titanium 1 sulfate. This thing down here, PB is lead. That has an unpredictable charge. OH is hydroxide. This is one of the polyatomic ions that do end in IDE, which is sometimes a little confusing because the elements end in IDE when we anion them. So this isn't talking about like hydrogen. It's talking about a hydrogen and an oxygen as a polyatomic ion. So just know that. Let's cut it in half. Needs to equal 0. Hydroxide, here's my hydroxide packet. It always has a 1- charge. And how many of them are there? There's 3 of them. So we're going to multiply it by 3 for an overall 3- charge. What does lead need to be to balance that out? 3+. How many leads are there? There's only 1 lead. Let's not put a 0 there. Put the inferred 1. So we take 3 divided by 1, which is 3. So lead 3 hydroxide. So much naming. And there's still more to come. But I think the second one is easier. I think the 2 nonmetals are simpler. So we'll leave it at that for today. Next week, we are gonna, as a class, go over some of the lab. So make sure you have your lab manual accessible wherever you happen to be doing your Zoom meetings. Just make sure you have the lab manual, and then we'll work together to get through some of them. If you have any specific questions, stay around. I know I've gotten a couple emails for people who wanted to chat, so please stay around. Otherwise, it is Wednesday. So I will see you next Monday. Have a good weekend. Bye, everybody.
These are recorded, right? So I can go back and watch what I missed today.
What was that, Carrie?
Are these, you record these lectures so I can go back and watch what I missed today?
Yeah, I will put them up tomorrow after my other lecture so that I can just put all the lectures on at the same time. So do you know where to find them?
Yeah, aren't they under like, what was it, Chemistry with Candace or something?
Yeah, just go to the Moodle page, and where you would hit the login button for Zoom, there's right underneath there's a link that'll take you to my YouTube channel.
Okay.
And they should all be organized by date.
Okay, great. Thank you.
Okay, Carrie. Bye.
Bye.
Hey, Sarah. You have a question?